Alright, Alright, so we've come to the point where, just like we did in the first semester where we set up talking about forces and then went and talked about energy, well, we're at the same point in the second semester. So we want to take what we've learned about electric forces and electric fields and use that to start talking about electric potential energy. So let's just remember a couple of basics from 221 here. So for starters, we said the definition of the work done by a constant force as you move from point A to point B is given by the magnitude of the force times the magnitude of the displacement times the cosine of the angle between them. So F here is our constant force, delta R is our displacement, and phi is defined to be the angle between the force vector and the displacement vector. Well, another definition that we talked about in 221 was the definition of potential energy. And again, we see that potential energy is, or the change in potential energy is defined to be negative the work done by a conservative force. So we said part of what's going on here is that we only need worry about potential energies for very special forces. Those very special forces are known as conservative forces. The conservative forces that we dealt with in 221 were the gravitational force and the spring force. They gave us the gravitational potential energy and the elastic potential energy. And all we're doing is we're adding a new conservative force here. The electric force is also conservative, so we're going to have an electrical potential energy. So to put these two things together, basically what sort of combining these two definitions tell us is that the change in the electrical potential energy is going to be equal to negative the work done by the electrical force, which is going to be equal to the work done by you. So you have to do work to move around charges in electric fields. The work you do directly changes the potential energy because the work you do opposes the work done by the electric field. So that's the idea. So again, thinking in terms of the field that we know best, how can we determine whether the potential energy is increasing or decreasing? Well, let's think about what we learned from 221. So we said, how can we determine whether any potential energy is increasing or decreasing? And so the definition that we came up with is the object moving in the direction the conservative force wants it to go. So if the object is moving in the direction the conservative force wants it to go, then the work done by the conservative force will be positive, and therefore the potential energy will actually decrease. So here's a situation where when we think about the electrical potential energy, if the electric potential energy is positive, that means two things. One, it means that the displacement is in the direction of the electric force, and two means that the electric potential energy decreases. If, on the other hand, the work done by the electric force is negative, again, that tells us two things. One is that the displacement is opposite the direction of the force. That's how we end up with negative work. But then that also means that the potential energy has to increase. The potential energy increases because the work done by the electric force was negative, but this negative sign sitting out front says the work done by you had to be positive. So you're the one that did positive work against the electric force that increased the potential energy. So if we think about the potential energy that we probably know best at this point, if you think about an object in the Earth's gravitational field, we know that there's going to be a gravitational field that points down. We know there's going to be a gravitational force that points down on any mass. And so when you move that mass up, the work done by gravity is negative, right? Displacement points opposite the direction of the force. So you've increased the gravitational potential energy. When you let that mass fall, just the opposite is true. So now gravity is doing positive work, gravitational force does positive work, and the gravitational potential energy decreases. Well, if we want to think about a charged object in a constant electric field, there are really two things that we now have to consider. Again, mass was always positive but charge can be positive or negative. So if the charge is positive, then we know that there's going to be an electric force that points in the direction of the electric field that acts on that charge. So if you let the force move with the electric field, that means the electric force does positive work, and you decrease the electric potential energy. On the other hand, when that force moves against the electric field, so my positive charge moves against the electric field, the displacement is now opposite the direction of the electric force, so the work done by the electric force is negative, which means you have increased the potential energy. Again, the only way to get the charge to move from here to here, right, our positive charge to move from in the middle in this direction to the left opposite the electric field, is because we have to physically move it. And so our physically moving it means that we do positive work to make the electric field do negative work, and therefore increase the electrical potential energy. Well, the other option we've got, of course, is that if our charge is negative. If our charge is negative, then we know that the electric force acting on it in the electric field it's sitting in point in opposite directions. And so now if I let it move with the electric field, force and displacement point in opposite directions, so the work done by the electric force is negative, which means it actually increases the electric potential energy. On the other hand, if I let my negative charge move against the electric field, now the force and displacement point in the same direction. So the work done by the electrical force is positive, which means we have decreased the electrical potential energy. So all this is very much in line, and again, you can come back and sort of remind yourselves, well, wait a second, what do I know about the gravitational field? Because electrical potential energy has to work exactly the same as the gravitational potential energy. All right. The other thing to point out is that all objects, you let them go and they will lower their potential energy. So if you give them the chance to lower their potential energy, all objects will. So if you let this negative charge go, it's going to naturally move in this direction. It's going to decrease its potential energy by moving against the electric field. To make it do the opposite of that, you have to do work to increase the electric potential energy. All right. So this means we can sort of summarize all this and say that for a charge in a constant electric field, right, I can basically calculate the change in the electrical potential energy using this expression. So negative Q is the charge, and notice this is not absolute values. So I'm just going to plug in, if it's a negative charge, I plug it in with a negative sign. E is the magnitude of the electric field, and delta X in this case is my displacement parallel to the electric field. So notice I don't care in this particular situation, I don't care how much the charge moves up or down because the electric field just points to the right. I only care about how much it moves left and right. And we define this delta X to be positive if it moves in the direction of the electric field and negative if it moves opposite the direction of the electric field. So this is one way that we can calculate the electric potential energy. What this means is that you increase the electric potential energy when a positive charge moves against the electric field. So if this was a positive charge and it moved to the left against the electric field, I would be increasing its potential energy. Or if it's a negative charge and moves with the electric field, that's also going to increase the electric potential energy. You decrease the electric potential energy when you do just the opposite. So you get a negative for the change in potential energy if I have a positive charge that moves with the electric field. So I need positive, 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 so this comes out negative. So that means I need my positive charge to move with the electric field or my negative charge to move against it. So this is one way that we can calculate the change in the electric potential energy as our charge moves around in a constant electric field. An alternative way to do this is, again, so part of what we're doing right here is we're kind of hiding a plus or minus sign in this delta X, and sometimes that can be confusing. So an alternative way to do this is to say, well, I'm going to just let this be the value of the charge. So notice my absolute value sign's back. I'm going to let this be positive. I'm going to let this just be the distance move, so this is positive. And now I'm just going to be the one who's responsible for the plus or minus sign. So the other way to sort of deal with thinking about whether the electric potential energy is increasing or decreasing is to say, conceptually, I know what sign I should end up with. Whether I'm making it move in the way that it wants to, that the electric force wants it to move, and so therefore the potential energy is decreasing, or I'm making it move opposite the way the electric force wants it to move, therefore the potential energy is increasing. So I can take care of the sign, and then everything else just needs to be plugged in as positive. I don't care which one of these two you use. They're both the same. You can use one, check with the other, it doesn't matter. Just notice in this case, Q, E, and D are all positively valued, and we're taking care of the sign out front. Which means that if you have a positive charge, you know that you're going to have an increase in potential energy if the positive charge moves opposite the direction of the electric field. So you got to put the positive sign in there. You know that the potential energy will decrease if the positive charge moves in the direction of the electric field. The opposite works for a negative charge. So a negative charge moving in the direction of the electric field increases its potential energy. A negative charge moving opposite the direction of the electric field decreases its potential energy. So either way works. I will probably use this way in class, but again, it doesn't matter to me which way you choose to use. If you want to talk about the electric potential energy, again, we have to have a 0 point. So the electric potential energy is really the longer statement of the electric potential energy relative to the point where the potential energy equals 0. So just like when we had a constant gravitational field and we said we could pick the point where we wanted the potential energy equals 0, if you have a constant electric field, you also get to pick the point in the field where the potential energy is 0. And so usually that's what we're going to do, and so the potential energy just becomes, well, again, plus or minus QED, where the distance you are away from the 0 point parallel to the electric field is what this D now is. And are you above on the positive side of it or below on the negative side of it, depending on whether your object wants to move in one direction or another. So this is all stuff that we'll play with in class in terms of thinking about what this means. Now the other way that we can deal with electric fields is to have electric fields that are due to point charges. So if I've got 2 point charges here, Q1 and Q2, I can think of this as, well, Q1 is generating an electric field as a source charge, and Q2 as a test charge sits in that electric field. And then I can calculate the change in the electric potential energy generated between these 2 point charges as K, Q1, Q2. Again, notice no absolute values here. I'm going to plug these charges in with their signs, and then I'm going to multiply this expression 1 over the final distance between the charges minus 1 over the initial distance between the charges. Those 2 distances are always positive. They're positive distances. So what this means is, if my 2 charges have opposite signs, so I know that there's going to be an attractive force, the electric force will then be attractive. If I pull them apart so that the final distance is larger than the initial distance, that means I'm increasing the potential energy. Again, they want to come together. I'm increasing the potential energy by making them do the opposite of what they want to do. If I let them come together, then that's going to mean that they're doing what the electric force wants them to do, and the potential energy will decrease. If my 2 charges have like charge, so they're both positively charged or both negatively charged, then just the opposite occurs. So here's a situation where they want to move apart. I have a repulsive force between them, and if I pull them apart, then I'm actually letting the electric force do what it wants to do, and the potential energy will decrease. If, on the other hand, I push them together, that's going to increase the electric potential energy, because that's the opposite of what they want to do. You want to talk about the electric potential energy? Well, really what you're saying is the electric potential energy relative to where the potential energy equals 0. And here, when we're dealing with electric fields due to point charges, the electric field equals 0 when you're infinitely far away. So what we're going to do is basically we're going to set one of these to be infinity. We're going to let the other one be the distance between my two charges, and so I can calculate the electric potential energy this way. K Q1 times Q2 over R. You'll notice this looks very similar to Coulomb's law, but there's some very important differences. So some important things to consider when you're thinking about the electric potential energy due to point charges. One is the potential energy can be positive because I've got the same charge. It can be negative because I've got opposite charges, or it can be 0 because my two charges are infinitely far apart. I do not take the absolute value of Q1 and Q2 to calculate the electric potential energy. I did when I wanted the magnitude of the force between them. I don't when I want to calculate the electric potential energy. Like the electric force, the electric potential energy depends on two charges. So I need two charges to interact to talk about the electric potential energy. But the electric potential energy is a scalar, not a vector. So it's like the electric force in that it needs two charges. It's not like the electric force in that it is a scalar. It's not a vector. This distance is defined to be a positive distance, right? So this is always a positive number. It doesn't matter where your charges are located. R12 is always a positively valued distance. And then notice that this is 1 over R rather than 1 over R squared. So the other fundamental difference with Coulomb's law is that the electric potential energy falls off like 1 over R rather than 1 over R squared. So all these are important things to keep in mind when you're calculating the electric potential energy from point charges. So if I've got a set of point charges, then again what I'm going to end up doing is saying, well, I need to calculate, right? I just have superposition that says the electric potential energy of charge 1 in this case is just the electric potential energy between 1 and 2 plus the electric potential energy between 1 and 3. So again, I've got two terms, one for each interaction that the charge I'm interested in has with all the other point charges in the area. If I want to calculate the potential energy of the system, well, basically then I just need to add in that third interaction. So I've got an interaction between 1 and 2, an interaction between 1 and 3, and an interaction between 2 and 3. So the electric potential energy of the system basically says, oh, I need 3 terms, one for each of my 3 interactions. And you'll notice that what this is it basically tells you that the electric potential energy stored in your system of charges is equal to the work required to build the system. So another way that we can talk about the electric potential energy of the system is to ask how much work did it take to put the system together. So when you brought in charge 1, charge 2, charge 3, you had to do work. How much work was required? That's going to be the same thing as the electric potential energy stored in your system.